Well, I think it's still a little bit. It so it's a little bit earlier. It is improving a lot now, but for a while it wasn't very clear how much it would improve, and so I wasn't sure whether travel was going to be possible at all. But now I am getting better, so I am really looking forward to the first time I will be able to go to a conference. But yeah, it probably won't be till the new year now.
Here in France, we are starting. We are kicking in. I already went to 3 conferences.
Yeah. Wow.
We are opening it. In the UK,
Yeah.
are you planning?
I mean, officially it is open, but case rates are still
Yeah.
extremely high. So yeah, it's a bit of a concern because the case rates are still so high. It's quite difficult to know whether things are going to be okay. It's a bit hard to know how whether things are actually going to get substantially worse. I mean, it's people are planning conferences for next year, but I don't think anyone is planning an in-person conference for this year just because the rates are so high that it's been difficult.
It's too much of a bet, I guess.
Yeah, I mean, it's been much higher than in Europe. So I think because of that, people have delayed any plans to do in-person conferences.
I think we are enough people, Susan. So I present you, and then you can start your presentation.
Okay. Sorry, sorry, I couldn't quite hear what you just said.
I say that we are ready, I think. So if you
fantastic.
want, I can present you to the public, and you can share
that will be
screen.
Great. Let me just get myself on the right slide. Just putting in a last minute video. And then, amazing. So let me just see if that will work. Is that looking okay?
Yes, looking perfect, I think.
And I think there's a speaker after me in the session, right? And the whole thing runs until 10:30. So
yeah. So let's start staying the timing. Let's keep maybe.
So if I aim to finish at about 8:20, would that be okay? It's 9:20.
I think it's going to be all right. Yes, even a 5 minutes more.
Okay, thank you.
Question, of course.
Yeah.
Okay. Good morning, everybody. So the first speaker of this morning is Susan Cox of King's College London. And please, Susan, start.
Thank you very much, Sebastian, for the introduction. And I'm very sorry not to be there with you in person. I wasn't able to travel, but I'm very excited to be able to talk about localization microscopy and present some ideas to you. And I'd very even though I couldn't come. So my talk's called From Images to Information, Enhancing Resolution and Improving Accuracy in SMLM. In fact, I'm going to almost exactly talk about the opposite order of things. So I'm going to start about improving accuracy and then finally think about enhancing resolution, but maybe in a slightly different way to the classic SMLM, where of course we enhance resolution by localizing molecules. But let's start there. And I'm going to think about SMLM maybe from a slightly different perspective that others will have presented it from, because I spend a lot of time thinking about information in images. And actually, this has led me over the years to actually start to just think a lot about what resolution might mean in this case of single molecule light microscopy. Because if we have a standard wide field microscope, it's fairly easy to say that the Abbe limit is related to the size of the point spread function. Of course, it is. The Abbe limit is given by lambda emission divided by 2 times the numerical aperture of the objective. Now, of course, this is determined, the Abbe limit is determined by the decrease in intensity between 2 spots at a certain distance. That is what Abbe considered to be distinguishable. Of course, whether you can in fact successfully distinguish 2 molecules at a certain distance depends on how many photons you have from them. Once you can do computational fitting, it starts to become a more complex question. But it's still a very good approximation, and in most samples you have so many molecules next to each other that you cannot successfully computationally fit them no matter how many photons you have. So let's consider super resolution. For structured illumination, we know we get at best half this value. So we can get down to half the Abbe limit. For STED, we can make a formula where the resolution is influenced by the saturation intensity of the depletion beam. But for localization microscopy, the resolution varies locally across your image with the properties of the fluorophores, distribution of the fluorophores, and the knowledge that's used in modeling the data. And I think in some cases where we have very low numbers of fluorophores, the concept of resolution does sort of start to not be very useful because we have 2 interlinked things in localization microscopy, the precision of the localization and the resolution, and at very simple structures, those 2 start to become entangled in a way that makes them difficult to pick apart from each other. So let's think about how these ideas about knowledge and information feed into localization microscopy. Well, in localization microscopy, knowledge is resolution, and this has been actually known about and implemented since the 1980s in image processing for microscopy, and most classically for deconvolution, where you say that you know the point spread function of a microscope and you try and use that knowledge to undo the process of convolution that occurs when an image is formed, and to therefore get back a more accurate representation of the sample. But as with all of these methods, it's really important to know exactly what information you're putting in, because the information that you're putting in will influence the result that you get out when you do your reconstruction. So this is a paper from all the way back in 1995 by Carrington et al. And here they are building in information about the point spread function. And this is the key sentence of the paper with regard to the information. We modeled the imaging process as consisting of a finite amount of data formed from a continuous object. And it's that phrase, continuous object, that contains the key assumption, which is that there are no breaks at length scales below the diffraction limit. And if there are, they will not appear in the reconstruction. So a reconstruction will give you a combination of the assumptions you've made and the structure of the sample. Now, if the assumptions you've made are all correct, it will give you the structure of the sample. If the assumptions you've made are not correct, it will give you back your own assumptions. So in localization microscopy, we take many, many images of the sample, and in each of those images, only a few fluorophores are emitting light, and then we use these, we localize individual fluorophores, and we reconstruct an image of the sample. So I think others have already covered how we achieve this blinking on and off of fluorophores. I can see that you had some lectures about it yesterday. It is a key component of technology, and getting those fluorophores to blink on and off so that they are well separated in each frame is the key challenge for getting good SMLM data. Now, once you have these localizations, you have to perform a fit. So you have to, in most cases, threshold your image, find individual patches, and then perform a fit to the data. So you're looking for mismatches between the data and your model. Oh, sorry. So that is where the improvement in resolution comes from in localization microscopy, from the fact that the mismatch between the data, which is your individual fluorophores which are appearing in your image, and your model, which is your point spread function plus some background, gives you a fit of the fluorophore position, which is much more precise than the width of the point spread function, which is what would limit you in a classic experiment. Now, it's not guaranteed that it's better. If you have a low enough photon yield, then you will get you can get a localization image back, which is at the resolution limit, or even worse. So it is just your photon yield with the influence of the background, which also influences your localization precision, which gives you your resolution improvement. But I've said that the getting the blinking to work well is one of the key technologies. And it's often been quite a challenge, especially in the second color channel, to get blinking data which is of equal quality. So this then brings us to the question, what happens if you are unable to get very sparse data, or what happens when we have cases where, due to the fact that the excitation of the fluorophores are stochastic, you might get overlapping fluorophores. And remember, this is a stochastic process, so there is, in any given situation, likely to be some degree of overlapping fluorophores. And we spend a lot of time thinking about this because it is a key challenge for the data, and because this process is stochastic rather than controllable, it's something you might well have to think about. And one thing we started to realize is that for a given excitation intensity, the probability of seeing overlap in your image depends on the sample. So the probability of seeing overlap in your image depends on what the structure of the sample is. If you have very small point-like samples, you're much less likely to get overlap than if you have an extended 2D sample. So for what I've seen shown here, a 0D sample might be something like small punctate regions on a T cell, possibly. Is 1D sample could be tubulin, and a 2D sample might be something like focal adhesions. Now, this might seem intuitive in that if you have a lower density of fluorophores in your sample, you're going to need to, you can excite a higher proportion of them. But it does have, but since we're often operating at the limit of how sparse we can make our images when we operate a microscope, it does have strong implications for how well different types of experiments are going to work. So if you were operating just at the limit where you were just able to get well-separated fluorophores in a sample that was very sparse, if you then changed to a 2D sample or even a 3D sample where you had some scattering Z, you are going to end up with a data which is much more challenging to fit. And in retrospect, that's probably why in early localization microscopy experiments, we all looked at very tiny punctate things or tubulin. So the reason that we have this variation, that the structure affects with how many fluorophores you're going to be able to successfully image, is that it affects the number of fluorophores that you cannot image in a given frame. So if we think about imaging one fluorophore in each of these cases, then we actually are not able to image a certain number of fluorophores in that frame, because if another fluorophore comes on within a certain radius, which would be, say, around 400 nanometers for a typical fitting process, then you're going to have an unsuccessful fit. And the number of fluorophores which you can't image varies very strongly with the structure of the sample. So if you have a small punctate sample, it'll be pretty a small number. If you have something that's extended, as we see here on the left, mine left, your left as well, trying to think how it will look in your auditorium, then you will have a lot of fluorophores that you can't image. And what this means is that the rate, the number of images that you require to get a reconstruction of a certain quality depends strongly on the structure of the sample. So you need a lot more images, in fact, about a factor of 100 more images to get a certain resolution in a 2D sample like a focal adhesion as you do for something that's just very punctate points. So this brings us on to in fact, to the idea of resolution. So here we had done this is some work we did quite a while ago where we modeled the expected outcome and then did some simple simulations where we assumed that all our fits were going to be correct. And you can see it kind of it kind of works okay. There's a bit of a mismatch, and actually this was one of the papers where we were very lucky and we got a referee who did not like this mismatch and who told us that it should be better than that. And I wasn't convinced because I thought it was quite good, but they were 100% correct, and they made us go back and look at it in more detail and really dig down into what was happening. So we have this feature where we know that we know from our model that we would expect to need a lot more frames for 2D systems. So what we wanted to do was to try and look at this in real experimental data or even real simulated data using a method to assess the resolution that we would be able to use in a real experiment. And the method that we decided to use was Fourier ring correlation, because it's really, there are some more recent methods, for example, from Alexandra Rashinovic, where they use some phase information, but at the time, this was the only method available. Now, Fourier ring correlation analysis, the basic idea has been in use in EM for quite a long time, but it was brought into localization microscopy by Bernd Rieger in this important 2013 paper. And what we do in Fourier ring correlation analysis is we take our original SMLM image, which is composed of many localizations. You split the data into two, so you randomly assign each localization to one of two images. You then Fourier transform each of those images, and you look at the correlation at a given length scale. So a Fourier transform is a representation of your image in terms of the length scales, where the center of the Fourier transform is the longest length scale and the edge of your Fourier transform is the shortest length scale. So what we are doing when we look at the correlation between these rings, so these rings in sort of light orange, is we are looking at the correlation between these two images on the second row at a particular length scale, and the length scale corresponds to the radius here, Q, from the center. The radius gives you the length scale that you are looking at in these images. Now, the correlation between these two images will fall off over spatial frequency, that is distance from the center, and at some point you decide that it's fallen below a threshold, and that is your resolution. And this is a really important way of assessing images in localization microscopy, because it does not rely on knowing the ground truth. In most biological samples, you will not know the ground truth, so you will not be able to assess against what you know should happen. Because after all, we're doing the experiment to find out what should happen. And they were able to do many important assessments using this, including how your resolution will vary with localization uncertainty and with labeling density. So this was really very important work. So we decided to use this approach to give us resolution values instead of doing our calculations. Now, if you remember, our curves went down, so the number of images required to achieve a certain resolution at a given activation density went down. Then we reached the optimal activation density, and then it went up again because we were not localizing so many fluorophores successfully at those high densities because they overlapped. But when we use Fourier ring correlation analysis, in fact, when we initially use it, what we find is that the Fourier ring correlation values always get better as the density increases. Obviously, this was concerning because this increase in resolution wasn't real, but I think it highlights that it is very challenging to assess localization microscopy images when you don't know the ground truth, because the types of errors that you get, in fact, tend to improve the resolution values that you get from, I would say, any of the assessment value methods. And so you get these improved resolution values, which aren't real, but not only that, the image will look better. It will have a higher signal to noise ratio because you are sharpening the image, you are increasing the signal relative to the background. So it also looks much more visually attractive. Oh, I think I have accidentally moved this video from an earlier point. This is an example of where I start out with a very low density and I'm gradually increasing the activation density. You can see that the number of successful localizations is very low at the beginning. And then as I increase the activation density, my number of successful localizations gets higher, and then gradually decreases again at the end, which is what I was showing in those graphs. So I actually started out a lot of my work in SMLM in high density SMLM, and I developed a method called 3B, which was quite well used, and I was very excited because I liked doing live cell imaging and I liked doing live cell SMLM. But I gradually started to realize that we actually had a bit of an issue with high density SMLM, which is linked to what I just showed you, which is that all the high density methods have a disadvantage. And here I'm going to show some stuff from our 2018 paper where we benchmarked against thunderstorm single emitter, thunderstorm multi-emitter, SOFI, and SURF. But I would emphasize that every
Susan, we don't hear you. Do you hear us? Yes, okay.
Yes, sorry, I just dropped off. I dropped off for a second. Am I back?
Yes, you can continue.
Fantastic, sorry. All of these high density methods have a disadvantage, which is that if the density of the raw data is too high, they fail, and they fail silently, which means that you actually get a pretty good value. You can get pretty good values out of your Fourier correlation measurements. You get a super res image, but it's something the algorithm has made up. And this is a classic image analysis problem. And it tends to occur with all image analysis methods in general. But in localization, it's maybe something that only tends to develop awareness of in the field over time. So I think a lot of people are very familiar with using deconvolution, but I hope that at this point in time, most people know that deconvolution can give you an artificially sharpened image under certain circumstances. It can give you artifacts in the background. And that's just a feature of if the algorithm is not working successfully. If particularly there are certain features of the data that can lead to this. But I think maybe we didn't have a lot of awareness in localization microscopy that we are going to have exactly the same problem. If you have high density data, there is an assumption that I will call the sparsity prior that tends to be built into methods that effectively means that if you have an extended area covered in where you have fluorophores lit up and the algorithm is trying to fit this, you will get fluorophores just evenly spaced along that area, whatever the actual structure is. And this is partly linked to the fact that most fitting algorithms use a Gaussian fit, and in fact, doing the Gaussian fit to the actual point spread function produces very tiny differences between fits of one or two fluorophores and makes it particularly difficult to distinguish whether there's one or two fluorophores present. And there are potentially some other ways to approach this, but I'm not going to talk about them today because it's hugely nerdy and detailed, and I think at this summer school we're just going to tackle the very broad brush issues. But if you are interested, feel free to drop me an email. So we have all these different approaches to high density localization microscopy fitting. And under the right circumstances, under a high enough activation density, they can all give inaccurate results. And I'm going to use a simulation of two parallel lines to demonstrate a lot of this stuff. So here in this diagram, I'm showing the parallel lines in red, which is my ground truth, and then the structure in white that you get back from the algorithms. And I would emphasize I am using two parallel lines because it is, unless you go into 3D, it is about the most difficult possible type of structure to resolve because it's extended in a way that gives you maximum overlap for a 1D structure. So what can we do here? So we developed a method called Haar wavelet kernel analysis, which is a multi-scale temporal filtering and lets you split fluorophores into different frames. So we take our input data and then you can split fluorophores which emit for 1 frame or 2 frames or 4 frames. And what this looks like is if you have input data like this, you can just split your fluorophore reappearances across multiple channels. And the effect of this is to decrease the density of the data that you have to fit. And it makes it much less likely to give you these sort of artifacts. It also has a side effect that because it's removing, because it's decreasing the density, it's removing any background of fluorophores that appear in the image, which means even if you have a sparsity prior effective in your fitting algorithm, it's not going to have anything to fit to. So we performed simulations and had a look at how this will perform for different spacings. And you can see that even though we're not always necessarily able to reproduce the structure perfectly, it at least gives you something that's the right size. So here in these last two at the end, I'm showing what we can achieve with Hawk. You can see it does show you the correct type of structure, pushes the structure apart so you don't get this artificial sharpening. And it gives you something that will give you an idea of your actual structure rather than pulling things into the center. So I think this is a pretty useful tool. It's freely available from the original paper. And we also tested it on experimental data. Of course, we are physicists, so instead of so what we did was we actually found a biological structure which looks like two parallel lines, since by this point we were pretty in love with the idea of two parallel lines. And we were able to show that Hawk was able to reproduce the structure. And then, since I love live cell experiments, we did some live cell experiments. Of course, the challenge with live cell experiments in trying to work out whether you're really getting back your structure is that they're live, and so they change. And so getting two images of something is pretty challenging at different densities. But Richard Marsh, who did a lot of this work, actually came up with a very good idea, which was to use a fluorescent protein that has two channels like MEOS 3.2 and look at both of the channels. So we look at the switch channel for our low density data and the unswitched channel for the high density data. And in that way, we're able to get both low density and high density data of the same structure. And we also did this for focal adhesions, though unfortunately this was MEOS 2 and we didn't get quite such good data. Focal adhesions being more extended are a lot more challenging. And we're able to show that we're able to get back the same type of structure using Hawk. And you can see it is quite a difference for these types of things. You know, using methods that are getting artificial sharpening, you will get back the correct type of structure. And depending on the method, you may get back the right size of structure, but you won't get back necessarily the details. And in fact, we used podosomes here because I had been trying to puzzle out with podosomes why our 3B results looked quite different to the fixed cell results. And we had been working on this for a long, long time, trying to resolve which one was the correct structure. And as so often, it turned out to be somewhere between the two. The fixed cell results were being affected by the secondary antibody labeling, and the live cell results were being affected by the data analysis. But I'm really excited that we were finally able to see something that I think is close to the actual structure. So the next thing that we thought about was, we have been thinking about a lot, is data assessment, because we've been using Bernd Rieger's Fourier ring correlation method, which I would certainly recommend anyone doing localization microscopy be familiar with. It is a very, very powerful data assessment method. But of course, you want to be able to assess your data, and we for other things as well, like artificial sharpening, and we wanted to try and contribute to that, and we felt that with Hawk we could do that. Oh, sorry, I added in one more bit, which is with data in Z. So for extended 3D data, you can also use Hawk, and it will improve it. We managed to get some very terrible 3D data, courtesy of Fan Huang, who took beautifully, inappropriately high density data of microtubules and mitochondria, and thank you very much to him for doing that. So what we decided to do was develop something that you could use to assess your images for artificial sharpening, because you don't necessarily always want to use Hawk, particularly if you have very low density data. There is a slight decrease in localization precision for using it. So what you really want to do is know whether you need to test your data, to know whether you actually have an issue with localization density. And we developed a method called Hawkman, which has in fact just been published in Nature Communications. And the software is, of course, freely available with the paper. And we take our test image, we take a reference that we've processed with Hawk, you flatten and blur those images, then you binarize and take two different types of threshold. Now you might ask, why are we taking these thresholds? And I will cover that a little bit later, but it's basically in order to, it's to do with the fact that in these images, obviously we have intensity on the way out, but the intensity doesn't correspond to the intensity in the sample. It is an intensity that we have reconstructed. So the question is then, how significant do we consider the intensity to be? Are we hoping for it to be completely linear or not? And there is an assessment method for images already that looks as to whether it's linear, and I will talk about that a bit later. We wanted to take a very complementary approach where we instead look at just whether the structure is correct. So we're not looking at how linear the image is. We are just looking at whether the structure reflects the structure of the sample. So we then take both of those images, both of those thresholds, and compare them, and we combine the information in them and correlate to give us a confidence map in how confident we are that the information is accurate and does not have artificial sharpening in it. And we can look and see at different lens scales, the different maps, and at the bottom, the confidence map, you can see that when we go to long length scales, we are confident about everything. But when we start off at short length scales, most of the image is red. We are not confident in most of the areas, particularly areas such as this and here, where we would expect to get high overlap, and then our confidence increases at higher length scales. So you're able to look at different length scales of your image and see, can I be confident that there aren't artificial sharpening effects in this image? And we tested this on different types of structure, and it seems to work fine. But I think we had one last question after looking at this, which is, are we just able to show people a comparison of the hawked image and the non-hawked image, which after all you could do visually? Are we able to do anything else? And the question that we ended up asking ourselves is artificial sharpening an effect that will show a difference even if the structure that you are looking at is below your resolution limit? So let's suppose you're looking at something which is just a little bit smaller than you can resolve with your localization microscopy experiment. Could you see a difference between an artificially sharpened result and a not artificially sharpened result? And we found that it does seem that you can. So you can take a structure which is below the resolution of your image. You can look with an artificially sharpened technique and a non-artificially sharpened technique, and you can then look at the difference between those two, and you will get information from the fact that you are seeing a difference between the artificially sharpened and the non-artificially sharpened result. And it will let you pick out structure which is just below the resolution limit in both cases. And in fact, we were able to show this in a real sample. So this is a mapping of the Z1, Z2 protein in sarcomeres, where because of the fact that sarcomeres are extended in Z, and with secondary antibody labeling, you just don't quite resolve it. You can just about see this split at the very, very edge, but in the center, we're not able to resolve it. But when we use the Hawkman software to test, we're actually able to see that there is missing structure because of the difference between those two images. And I thought that was really exciting. And finally, we also made a map of the length scales at which the information is accurate. So this is available to try right now. It was up on bioRxiv. It's also up on Nature now. And you can download the software and use it, and it can give you maps of how accurate your image is. And we're very excited to share that with you. So I did mention that there was another technique that was used. In particular, it's called Squirrel. It's a method that was developed by Sean Cully and Ricardo Enriquez at UCL. It looks at how linearly related the wide field image is to a downsampled version of the localization microscopy image. And that is really useful because it gives you information about how linear your image processing technique is, and it tells you about whether there's any structure missing at the scale of the point spread function. So this is a really useful technique if you want to see if you're missing complete areas, in particular, say, if you are ending up with stuff which is just getting cut completely because your fluorophores are not switching in the expected way, or maybe due to non-uniformity in the illumination, you will see that in Squirrel. And you will also get information about how linear it is. Now, this can be very important, particularly if you are using a non-linear technique, like maybe Surf and Sophie. They will introduce non-linearities. Now, that may or may not be important, but you probably want to understand what they're doing. So we have these three techniques, which I think are still the three main ones. We have Squirrel, which can tell you about missing structure and the linearity of the relationship, and it can map that. We have Hawkman, which can tell you whether you have artifacts in your image and whether your data is becoming biased. Sorry for anyone, I guess everyone knows what a squirrel is, but if you don't know, Brian Blessed played a Hawkman in Flash Gordon. Possibly not everyone has seen Flash Gordon, but I hope you all appreciate what an amazing mascot we have in this guy in a suit with large wings and a sword. And then, of course, we also have Fourier ring correlation, which can actually give you a number for your resolution. And there have been later updates, particularly, as I say, this most recent work from Alexandra Radjanovic, which allowed us to look at the effect, to use phase to get us better information about the resolution. So I see I have managed to talk until I'm almost out of time. So I am gonna, in 4 minutes, try and cover what I talked about improving resolution, which is our latest work, which is extracting structure from multiple images. And this is some recent exciting work that we've been doing with deep learning that I just wanted to share with you at the end as a sort of side note to the main issues I've been talking about. So we often have multiple instances of cell structures, and people have looked for a long time, particularly starting with nuclear pore complexes, to how the information from these images can be synthesized. And I started thinking about the fact that we have various factors that influence this. So we can get 3D data quality, but it's often the third dimension is less good than 2D data quality, and often getting that third dimension compromises the in-plane resolution. We can fit a model, but then that constrains the possible outputs. And as I've been talking about, building in information limits what you're going to get out. But you also have the challenge that unconstrained fits are very, very slow and can be prone to local minima. So we've recently developed some work that was, I think, published last week, where we use deep learning to allow fitting of rotations of a 3D structure to 2D data, while also allowing unconstrained fitting of an arbitrary model. And I'm showing here the structure of the deep learning network. We have our input images, which are all our localization images. And then we have our reconstructed 3D matrix. And what we're doing is we're fitting we have our model, and then we're actually using the deep learning to learn the rotations for each image. And then we generate some images and compute the loss. So what we can get is we get a series of images, and we then attempt to reconstruct a 3D structure. We're using here the Stanford Bunny, which is a classic test system in computer vision. And I guess the other trick that we use is we start out with very blurred images and then gradually take down the blur. And here I'm showing pairs of images, on the left the input and on the right the output. And you can see we're able to get back a very accurate model of the sample. So these in the wrong order. Here we go. This is our fit of the rotations. You can see it's not perfect, but it's able to get a pretty good fit to the rotations of the bunny. And it's the deep learning network is able to do this much more efficiently than a standard fit would do, because it's able to make good smoothness assumptions about the phase space. And what we get is something like this, where we start out with a uniform model, and you can see the structure gradually emerging. You can see it wobbles around for a while, and then it coalesces. Now, you can see that the rotation of this particular structure is completely arbitrary. And that's because we are fitting this 3D structure to every single image at a different rotation. So all we know is that we have some structure that looks like this. And I think this is pretty exciting, because I think unconstrained fits are a really good idea, because we allow them to be anything. We were able to look at the impact of various parameters which are going to influence any localization experiment, particularly scatter, which is obviously a big issue, and labeling efficiency. So in both cases, we're getting worse towards the right. As the scatter goes up, our fit gets less good, as you might expect. As we have fewer fluorophores, our fit gets worse. And then we did a test reconstruction fit to experimental data of CEP152, which is a centriole protein. And you can see that we're able to get back the toroidal structure that Ciliana and Christian got back in their original paper, but without providing any constraints at all on the structure of the sample. So I'd like to thank all of my collaborators, all of my group who did this work, and you for listening. Thank you very much indeed.
Thank you. Are there any questions? Maybe I have one. You mentioned quite at the beginning that there is an optimal density. Can you elaborate on this concept to explain how to choose it and how to tune it?
Sorry, I'm not quite able to hear you. There's a bit of an echo.
You mentioned that there is an optimal density of fluorophores.
Yeah.
Can you elaborate on this and explain us how you can tune it and why it is optimal?
So the optimal density is it's the density at which you have, so it's the density at which you are, the number of fluorophores which you are losing to the fact that fluorophores overlap is still just slightly less than the number of fluorophores you're gaining by increasing the activation density. So you can theoretically calculate it. So we have that in our 2017 paper. So in a fluorescent protein, a switchable protein experiment, you can influence this very directly using your 405 nanometer switching laser. And in fact, we did that in that paper. You can just increase your 405 nanometer light to increase the switching. It is difficult to quantify because as you start to get more overlap, your results out are less accurate. So you would probably have to do something to separate the fluorophores to be able to assess it. That's why people generally try and go on the very low side. But what you can do is you can start at the lowest density, assess it, and then gradually increase until you get to the density that you think is optimal. In D-Storm, which I know a lot more people will do, it is more challenging to effectively control the fluorophores. But I think now still what is most commonly used is you use your preferred buffer, and then a lot of people now, and Jonas Rees might have talked about this a little bit, is you can tune the blinking using your the laser that you're using to directly illuminate the fluorophores to collect the light. So you can decrease the illumination intensity slightly, which will decrease the amount of time that the fluorophores are spending in the off state. So it'll give you slightly more dense data. So, and you can also, of course, extend your exposure time. So you can play with your illumination and your exposure time to tune your the activation density in each frame.
Thank you. Okay, I think there is one question, yeah?
Hi, Susan. Thanks very much. So I really like the last idea of guessing the 3D from the 2D. But how do you think it would be doable in practice if you have no idea or just a little idea of the model you are looking at? How do you think it could be applied in practice if you have no idea about what you are looking at? Can you guess the?
You mean how do you assess how well it's done, or?
Yes. How can you I don't know, from your model extrapolate the 3D from a 2D projection if you have no idea of the biological structure you are looking at?
So what we did in the results that I've showed you is we just start out with an arbitrary model and then we allow it to optimize. But I presume your question is really how can we know that it's a reasonable result? And I think this is really a question sort of also that feeds back into this general issue for localization microscopy. How do we know that our result is reasonable? I think it's important to note you do still have the 2D data available. So what we can do is we can assess how well our model fits the 2D data. And we actually, in fact, started out by just looking at that by hand. Now, that's very easy to do in clean model data. It's not so easy in messy localization data. And I guess I also want to do it in the 2D because I'm sure you know, assessing 3D models against anything is not a very well-defined problem. Even in the computer vision world, it's still a huge challenge. There isn't really an agreed upon approach. So I guess I don't know. I think it's still an open question. But I think it is really also an open question when you have models. Having the model makes it easier in that you can say how well it's fitting the data, but it still doesn't tell you how accurate it is to the actual 3D structure. So I think in some ways what our approach does is it just makes the fundamental problem more apparent. But I think it is a really interesting problem that we want to think about more in the future.
Okay, we thank Susan again, and we pass to the next speaker.
Thank you very much, Sebastian.
Donc la première, c'est n'oubliez pas qu'il y a un concours photo en route. N'oubliez pas, j'ai besoin de toutes les réponses pour le questionnaire que je vous ai envoyé hier pour le repas de vendredi. Pour ceux qui n'ont pas de mug, on va faire une distribution à 10 h dans le hall d'entrée. Et puis la dernière info qui vous plaira le moins, c'est qu'on va réduire à partir de maintenant, enfin à partir d'aujourd'hui matin, on va réduire la pause et on reprend à 10h30 en salle Méditerranée. Et ce sera tous les matins comme ça. Je suis désolé, mais on a vraiment besoin de récupérer quelques minutes par-ci par-là. Donc voilà, merci. Il y en avait encore une autre. S'il y a des gens qui ont besoin d'organoïdes, il en reste. Donc si vous avez envie de faire des manips dessus, vous pouvez en récupérer.
Okay, thank you. I introduce to you Johan Schechtman, which is professor in Technion in Israel. Pardon, s'il vous plaît, monsieur. La lumière, c'est possible I think this one is better.
Hello. Yeah. Okay, good morning. So, first of all, I would like to thank the organizers for inviting me to this unique conference. It's really inspiring what you've done here. So it's a great opportunity. Thank you. Okay, so my talk is titled 3D Localization Microscopy by Deep Learning. Or how and why to ruin a perfectly good microscope. Okay, so let's dive into the details. So my talk deals with localization microscopy. Now, all of you have seen a lot about this in the last day, but in case someone was at the beach yesterday, I will explain very quickly what I mean. So localizing particles comes up in two main situations in microscopy. One is tracking particles, like here, where you see a single protein labeled with a fluorescent molecule, diffusing, doing its thing on a cilium of a cell. And we are interested in obtaining the trajectory, which is the position over time. Okay? And you can obtain this trajectory to very high precision, depending on the signal to noise that you have, of course. But anyway, a precision that is better than the width or the size of the PSF, simply by localizing the position in each frame, for example, by a 2D Gaussian or a model of the PSF, and then you get this trajectory. Okay. And the second application that now everybody knows is localization super resolution localization microscopy. You have your sample, it's labeled with millions of fluorescent molecules. You make them blink. Over time, you fit each one of these molecules, and you find the position, and then you build up this extraordinarily high-resolution image, typically a 10-fold improvement in resolution. I mean, great. Super resolution, there is a Nobel Prize about it. Okay. Now, the problem is, well, one of the problems is that the perfect picture that I told you about is that you have a nanoscale emitter, you have your diffraction limited spot, you fit it with a model, you can have very high precision because if your model is correct, then you're just mostly limited by the signal to noise, and it's great. But in reality, we have this issue that came up in the last talk by Susan Cox. And the issue is that you can have overlapping emitters at low signal-to-noise ratio, and you still have to deal with this somehow. And this will only become worse if you increase the density, of course, of the imaging, because you want to improve your temporal resolution. So over the years, people came up with various solutions to this problem, and even our previous speaker did a lot of work on this. And some of these approaches work very well, and they can handle this kind of data. And the challenge is, the problem is that they are slow. Some of them are painfully slow, some are less painfully, but they're all slow, even those that work very well, and they require parameter tuning to playing with thresholds and so on. So a few years ago, we realized that it's time to solve this by deep learning. You know, when I say this now, it seems obvious because there's so much work that has been done on this. But at the time, you know, someone had to do it. So the idea was to take to train a neural net encoder decoder that takes these low resolution images and outputs the positions of the fluorophores. What it really outputs is a oversampled version of this, with ones where there is a fluorophore, or at least where we think it is, and zeros elsewhere. And so the idea was to just add up all these images at the end and obtain a single super resolution image. And that's what we did originally. After we did it, people started asking, why can't we get the localizations, the positions of the fluorophore? We said, okay, if you want the positions, you can also output. So now we also output the positions by locally fitting these. So the short story is, it works, and it works very nicely. You train this on simulated images. So we have the privilege, unlike other problems in bioimage processing, that it's pretty easy to simulate 2D images from a microscope of localization microscopy. You come up with you randomly select positions, you put fluorophores there, you convolve with your PSF, you add noise, and that's it. So we can have thousands of random images like this as our training data and the ground truth. And by the way, we also did some experimental training. How do you obtain ground truth for an experimental image like this? So this was semi-automatically. We took a bunch of sparse images, we localized them with an existing algorithm, and we summed them together. Okay, then you have your ground truth high density image. Okay, so the cool thing is it's very fast, because the inference is very fast, and it works very well. How well? You can get to a density of about 6 meters per micron squared, which is at single molecule SNR, which is pretty high. Okay, we then collaborated with the Enriquez lab, and this is available online through the Google Colab, so you don't even need a GPU. We heard about this a bit yesterday. And I have to say there is a lot of work on this field. You heard some of it yesterday. You heard about CARE, you heard about Decode, and some of these others. Okay, some of these are also extendable to 3D, which is what I'll talk about next, with even some improvements over what we did. So 3D. Samples are 3D, you know, many samples, and if you want to track something or to image, to get a super resolution image, SMLM image in 3D, you have to somehow deal with this fact. What is the problem? The problem is that when you have a point source and it's in focus, this is a microscope, by the way. When it's in focus, you see a nice spot. When it's out of focus, you see a blur. And this blur has 2 problems. First of all, it's kind of symmetric above and below focus. With some noise, it's more of a problem. And the other problem is it has a very small depth range. So if you want to image something more than a micron, or maybe even half a micron in thickness, you're going to have a very hard time. Now, over the years, there have been some very many solutions to this problem, how to image things in 3D in a microscope. Like biplane, we're going to hear about multifocal planes sometime. I saw, sorry, on the program. And other solutions, I will only concentrate here on the following solution, which is what we like, which is point spread function engineering. And here is the idea. You take your perfectly good microscope and you ruin it by putting a phase mask in the optical path, in the detection path. What this does, if you put this kind of mask, for example, which is called the double helix mask, your point spread function no longer looks like a point. It looks like, in this case, 2 points that rotate as a function of the depth position of the emitter. So if it's above focus, it looks in this orientation, and below focus, it's this orientation. And then what do? You analyze this image, you process this image to extract the X, Y, and Z position of the fluorophore. So this filter sits in the Fourier plane of the microscope. Therefore, this is a shift invariant system. So this means that this shape would look the same, okay, up to field of view aberrations, all over the field of view, right? So you can get different spots, pairs of spots, and so that is going to tell you X, Y, and Z will be determined by the orientation of the two spots. So now, when you look at this, you say, okay, so when I first look at this, so this is very cool, okay? Then the second question I asked, well, the first question I asked, and I heard this question yesterday, by the way. I had a déjà vu. This is a French word, so there is a workshop here on PSF engineering, the Zola 3D workshop. So I recommend it if you want to see how this is done. And then someone asked, I was visiting there, and someone asked, wait a minute, why are you using this shape, this phase mask? Why 2 lobes rotating? Why don't you have 4 lobes or some other shape? I say, yeah, and this is really the question I asked 10 years ago. And here is the answer. So the answer is, well, this was kind of historic. This phase mask didn't come from microscopy even at all. It came from wavefront shaping. Then some clever people realized it can be used in microscopy. But if you then ask the question, wait, I have the freedom to design whatever phase mask I want. What do I want to design there? Then you have to ask, okay, what do I mean? What is my purpose? My purpose is to encode the information in the most efficient way. I have a limited number of photons, and I want to spread them somehow on the camera such that I will have the best precision when I localize X, Y, Z. And it turns out that it matters what phase mask you put here. Different phase masks contain a different amount of information. And this can be quantified. If you look at estimation theory, there is something called Fisher information. And Fisher information tells you how much information your system contains about a parameter that you're interested in estimating. In our case, the parameter we want to estimate is Z, the Z position of the molecule. You can think of some very bad phase masks to put here. For example, some of you know the cubic phase mask that is invariant to Z, or the extended depth of field mask, which is invariant to Z. We are looking for the opposite. And if you solve this problem numerically, because I don't know how to solve it otherwise, you get this mask. The tetrapod mask, simply by optimizing the Fisher information of the system. And it tells you this is how you want to spread your photons, such that you have the most amount of information about the 3D position of the emitter in your system, assuming Poisson noise, which is a pretty good assumption. And by the way, you can also you can solve this optimization problem for different depth ranges. So you can have one tetrapod for 3 microns, 4 microns, even up to 20 microns. And now it's important to say, when I say that the range of a PSF is 20 microns, what does that really mean? So if you have enough photons from a point source, then you can localize it probably with any PSF. Okay, so the challenge is over a very large Z range. Even with in the standard microscope, you would figure out an algorithm to fit it if you have enough photons. So the challenge is that you have a limited number of photons. Okay, and then what is the most efficient way to do it, to give it the best precision? Okay, what is this phase mask? This is an exotic element. All the other elements here are pretty standard in microscopy. So it's a piece of something physical that has to delay the phase of the light in different positions. How do you do that? Well, here's one way. You take a piece of transparent material like a glass, and you etch it chemically, so that you have different layers, okay, different thicknesses, and then when the light hits each one of these pixels from the bottom, it propagates and acquires a different phase, optical phase, and then you have some wavefront at the end, which is what you wanted to shape. Okay, so you show here, see different thicknesses of the pixels, light propagates and so on. So in the air, it's the same velocity, and then you have a different velocity in the material, and then you have a different phase at the end. And this is the equation. So the refractive index of this material is about 1.5 usually, if it's glass or similar. Air is 1, so this is about half, the first term there. And then the delta H here, or is the difference between the thickness of the pixels. Where should I will point here. I'm sorry, guys. I'm pointing here. So so the thickness is different and so on. And this is important because of what I'm going to show you next. So the thing is, it's a pain to create these masks, because you have to go to a clean room and etch with lithography. This is a painful and expensive process, and time consuming. But you can still fabricate it. Here's an example. Okay. Important point. Why do you have to do this with lithography in a clean room? Because the difference between the pixels has to be very small, because it has to be on the order of fractions of a wavelength. So, tens of nanometers difference. How are you going to do this? Only with lithography. Okay. So one way is this phase mask. Another way to generate, to apply this phase mask is with a programmable array, a liquid crystal spatial light modulator, which is really great because it's programmable. Unfortunately, it kills half of the light because it only works on one polarization, and fluorescence is not polarized. So that's a problem. But here is a new thing we're doing. We are 3D printing these things. So now, if you have any experience with 3D printing, you can ask, how can you 3D print something at a resolution of tens of nanometers? The answer is we don't. There is a trick around this, and this is the trick I want to tell you about next. So this is one of those 3D printing based phase mask. And here's the idea. It's true that if you have your diffractive optical element in air, then it has to have very fine feature, because the refractive index of glass is much bigger than air. Okay, so that's the reason I told you have to have very fine features. But the only thing you care about is the wavefront at the end of this thing, at the output of the DOE. So what if you could replace air with something with a closer refractive index to the DOE? Then effectively you have the same wavefront at the end, but you can scale up everything. How much can you scale up? By the amount that you can match the refractive index of the liquid to the glass, or to whatever material you're using. So this is kind of a crazy idea, but it works. Okay? And the cool thing is, not only you scale up everything, the error, the robustness also increases. You can be off by microns, where previously you had to be off by nanometers. So we do it. So how do we do it? We actually 3D print a mold, a ceramic mold, worked the best for us. We fill it with polymer, transparent polymer. We put it in a little aquarium, and that's it. That's our phase mask. So we took the only exotic element we had and replaced it with something that's very easy to fabricate. And this is published, and please ask me if you have questions about how to do it yourself, because we're trying to democratize this technology as much as possible. So, what do we do with this? Well, what do we do with phase mask? We track things in 3D. So here's an example. You have a cell labeled, all of the telomeres are labeled with telomere binding proteins. And let's say you want to track them as they move. I want to see all the telomeres in the cell. Why? Because I'm interested in the diffusion statistics of them under certain conditions. For example, we're now looking into the cell cycle dependence of this diffusion. You see, with the standard PSF, some of them are out of focus, you don't see them. Using our tetrapod, you see all of these telomeres. Each shape here is different because each Z position of a telomere is different. But you immediately see the problem, which is overlap. Okay, we heard a lot about overlap in 2D, but in 3D it's even worse. First of all, the PSFs are big, and second of all, you don't only have to find each one, you have to also fit each one to a different shape. So it's algorithmically, you can imagine it's a more difficult problem, and it is. So fitting something like this is a problem, wasn't solved in the past. But you know where this is going. We solve this with deep learning. And it works like this. Similarly to simulating 2D images, you can simulate 3D images. All it takes is a very, very, very good model of your imaging system, which we have. Well, we have a very, very good. And the extra very comes from the fact that we can fine-tune the model by taking an experimental Z-stack, doing phase retrieval, and obtaining an even better model of the system. So anyway, you simulate random positions. This is a different network that outputs a volume of localizations. But again, it's the same idea as the 2D problem. Okay. Now, and again, you train it on simulated images. Here are the telomeres from before. This is the reconstruction that we get from this image. And it works very well for this kind of density. Still not perfect. I will show you next how we improved it even further. But first I will show you SMLM data. So remember SMLM 2D, this is SMLM in 3D. Each shape here is a single molecule in gray. And in purple you see what the network understands. So the network reconstructs the positions it found in gray. So you see it's a very good match. And indeed you get nice 3D images of this sample was mitochondria. As you can see here, Z range of about 4 microns using our tetrapod. Now you can say, okay, I was telling you these stories about how we can design the optimal point spread function for some application. So you can ask me, if you do that, why are you using this big tetrapod PSF for imaging this kind of sample where you have such high density, like in the SMLM problem, or even in the telomere that I show you? Maybe there is a better PSF to use. And to that I answer yes, there must be a better PSF. Because the tetrapod, I remind you, was optimized for a single emitter. This is really not the case here. But then the question is, how do we find this best PSF? I can define the problem. I don't even know how to define this mathematically. And it's really difficult to answer this in a general way. So we resorted to find this optimal PSF, to let the neural net learn this PSF by itself. Okay, so now we're saying, neural net, you're not only responsible of decoding the information, you're also responsible of encoding it such that the decoding would be optimal. Okay, and you do this by adding a layer to the net in principle, where each one of the pixels in this phase mask is a learnable parameter. And then the net simulates what's going to happen to the PSF as it changes these pixels. So this is the result. And you see the net learning how to optimally encode this information. And the strategy is, okay, we let the net do what it wants to do. We take this result, we implement it, and that's it. We have our optimal system. And the net that will recover the information. And indeed, if these were the telomeres before, now they look like this on the right. And you can quantify how many of these telomeres you were able to localize, and it's more. So the results improved significantly. And immediately you see why, because the density is much lower, so any algorithm would have a better time with this, with the right side type of information. So then what the net really did is it found its compromise between encoding the information, so it has to modify the PSF as a function of Z, but it can't let it get too large. And this is the compromise that we don't know how to find optimally otherwise. Okay. Oh, by the way, it really looks like a hummus plate. So, okay. So that's the informal name in our lab of this mask. So you can track, now these are telomeres being tracked with this hummus mask. And you get these 3D trajectories of all of the telomeres, and we're really happy. So a question I was often asked about this, is it worth it to split the information into two different channels, two different optical channels? Why are you using just one PSF? Why don't you use two? Okay. So it's a good question. The problem, of course, is you're losing signal to noise because you're splitting the photons. What are you winning? Well, you could be winning information. Because if you had some orientations of positions that were overlapping in some encoding, maybe with a different encoding, they won't overlap anymore. Yeah, so the answer is yes, you actually can do it, and you do win at very high densities. It is worth, and reasonable SNR, it is worth to split into two channels. So the same way we learned one channel, we can also learn two channels. We let the net decide how it wants to encode in two channels, and this is the solution. So it's learning these really complementary patterns, which is cool. We never told it to do it, but it found this way. And if you look at how the information is really encoded here, you will see that the position of a point source is encoded mostly in the relative position in each of the channels. So it's kind of like one spot. There's also some shape, but like here, it's just one spot. But because you have the two channels, you can see where they are located with respect to one another. Okay, you can, in principle, register the channels and see where they are. Okay, so now you can deal with really high densities. This is a higher density of telomeres than before. We have the two channels being imaged, and we're just observing the telomeres diffuse. So this is the experimental data on the top. Two channels with the two different complementary PSFs, and these are the telomeres diffusing. So, how am I on time, by the way? You don't know? When does it end? I have time. Okay, I have time. So, here's another cool thing, which is multicolor. So, you know, in fluorescence, we often do multicolor imaging because we need context, right, of different things. So, how do you get multicolor? And how do you combine it with PSF engineering? So let's say you have different particles at different colors. You want to track them as they move. Well, normally in microscopy, you split into channels. You have a filter. It splits into green and red, or you switch a filter in time. But I'm talking about wide field microscopy. But we thought you can do the whole thing on a single channel if you only encoded the color of the emitter by the shape of the PSF. And here is a simple way to do it, relatively. You take the same phase mask, 3 copies of a phase mask. You put them, you split the light into colors, and each color goes through a slightly different rotated point spread function, mask. Okay, so you get this tetrapod, and by the angle you can determine the color. You don't see any color. You just do computational analysis on an image that looks like this, and it's, okay, this is the angle, so it's an orange one, and you also know this XYZ position as you did before. Okay, so so here are some 3-color beads just diffusing around, and we can, from the single image, you can see 3 populations of beads. You can determine their positions. So that's cool for beads. You can do this in, this is yeast, where we label the DNA in 2 different loci. For different purposes. This is this fluorescent repressor operator system you can use in yeast very efficiently. So there's like 100 proteins, GFPs and M-cherry. And what you see here is actually, you see these guys are green, these guys are red. And actually we had some shift, intentional shift between the green and the red channels. So actually this and this is the same cell, and this and this. Okay, so this and this. Okay, so you can determine the 3D positions of these loci over time, which is what we care about. We looked at the distances between the different loci. But actually, there's something cooler you can do with color PSF, color-related PSF engineering, which is the following. I told you about these phase masks. You can also do it with the liquid crystal SLM. Whichever way you do it, you use a phase mask, it's always going to be wavelength dependent. So a green light will experience a different phase delay than red light, just because of physics, even with no material dispersion. So what? So it means if you don't do anything, you take a phase mask that was designed for green, you illuminate red fluorescent through it, you will have aberrations. And this could be a problem, but it could also be a feature if you use it correctly. How do you use it correctly? Well, so by the way, this is the phase, the wavelength dependence of the phase. So this is the phase on the SLM as a function of voltage of red light and green light. You see, it's a different curve. So how do you exploit this to add some information to your system? Well, here is how. You design a voltage, in this case, voltage mask. With a DOE, it would be just a height mask, such that red light will experience one phase mask and green light will experience a different phase mask at the same time. Okay, you can think this is nice, but will it work? How much freedom do we have in design? Because they're obviously related. You can't do just anything you want. But it turns out you can almost do anything you want. This is an experimental image of this phase mask, of voltage mask, looking at a red bead and a green bead. And this is what you see on the camera. So the PSF is the word red for red color and the word green for green. So there is freedom here. So you can take this and design rotated tetrapods for red and for green with the same voltage mask. Let them pass through the same mask, and you can obtain populations of different colors on the same channel without any spectral filtering. You pay a little bit in SNR. This is why this looks like this, because it's never perfect, this trick, but in principle it works. Okay. And very briefly, you can also learn the optimal way, the optimal PSF to distinguish between different colors, right? Because, so this is the net learning, a voltage mask to distinguish between 4 different colors. And these are the 4 different colors. These are quantum dots, I think. Yes, these are quantum dots on a cover slip. And they have different emission spectra, and the net picks up on the different colors. It misses a few because this is a really difficult problem, because the PSFs are kind of similar. And this is only in 2D, by the way. Okay, finally, if you think of the experiments I've showed you about tracking, you see there is a problem with throughput. The problem is, it's not just unique to PSF engineering or anything, but the problem is if you want to do microscopy on cells, you have to look at many cells if you want to get any quantitative data. And it will always be advantageous to increase the throughput of your system. And for example, the yeast experiments that I show you are based on the work we did a few years ago, where we had to image the distance. We imaged the distance between pairs of loci for hundreds of cells, and this took days. Okay, we didn't have any fancy automated throughput systems like other groups, but still it was very time consuming. And we thought, how do we make this much faster? And so how do you measure 3D distances inside cells at very high throughput? And the beginning of the solution was right under our nose. We have in my building an imaging facility, and they have this image stream system. Image stream is an imaging flow cytometer. So you flow cells, and unlike just flow cytometry that gives you a fluorescence value, it gives you an image. So you get an image per cell. This is great. This is really just a microscope that's looking at flowing stuff. But it gives you thousands of cells per minute. Now, in principle, you can label whatever you want to label and measure the distances between them. But what is the problem? Well, the problem is you get a 2D image, because it's a commercial device. They have a 2D. So upon realizing that, we said, okay, let's modify this device. We went downstairs to the imaging facility. We knocked on the door. We said, hello, you know this 600,000 device you have? Can we open it, please? They were really kind to us. They said, and amazingly, they said, okay. So this is a message to imaging facility people. Be friendly, it could be worth it. And message for the students, don't be afraid to ask. If you want something, just try. I thought it would be 50-50, but okay, they agreed. Anyway, we hacked this machine. We opened it up. We didn't tell the company, so warranty was not harmed. And we looked at, okay, where do we place a phase mask? So we had to do some reverse engineering. This is a wonderful machine, by the way. It gives you 6 spectral channels in our case, and beautiful images. They synchronize it very well. There's even no motion blur. So it's great. Okay, we find where we place the phase mask. And here it is. So we first put a cylindrical lens. And now these are beads flowing. And you get, astigmatism. This is elongated along one way if it's above focus, or farther from focus, or closer to the objective. You have 3D. We can do this. Okay, so now you have, these are yeast cells. You have the YFP channel, the M-cherry channel. You fit them, you get the 3D positions. But now you can do this thousands of cells per minute. And you can build a histogram of 3D distances. So it's really extremely efficient. We were interested in what happens to this distance under 2 different galactose sugar conditions. So with galactose and with dextrose, and we see different distances. And the cool thing is you can get such a measurement in minutes. So this means now you can look at the population level change over time. Okay, of the 3D distance between spots inside the cell over time, because each minute here is thousands of cells. So you can get such statistics. You place the cells in galactose, you let them flow, and you see how over time the population level changes. You could never do something like this in a normal microscope, because you wouldn't be gathering enough information in a minute to do it. Okay, so that's about this. This work was led by Lucian Weiss, this guy. He's my former postdoc, and he's now in Montreal, hiring, by the way. So it's a good place, great lab. They speak French there, I heard, so formidable. So now, okay, I think this is it. This is to summarize. I hope I convinced you it could be worth it to ruin a perfectly good microscope. With PSF engineering, you can do localization. I haven't shown you surface profiling. If you like surface measurements, then you can extrapolate from what I told you and imagine that you take a surface and you cover it with fluorescent beads and you just look at it. And if it's dynamic, you can track the dynamics of the surface. This was published last year. And by the way, final note, you don't even have to ruin your surface by covering it with beads, because we are not always allowed to do that with our surfaces. If it's reflective enough, you can illuminate it with an array of spots. And each spot will behave as a point source and will be modulated by your phase mask. Okay? But it has to be reflective enough. And this is more challenging. I showed you some cool things you can do with color engineering and high throughput with the imaging flow cytometry. So with that, I would like to thank the group. This is the group a couple of years ago. And thank you for listening.
Hi, thank you for your presentation. Very interesting. So I have a question about the estimation of your PSFs. So I'm sure you looked at that. You estimate your PSFs. So how robust is the estimation of your PSF? So does it all?
I can hear you. So the question is about estimating the PSF. So do you mean estimating the model of the PSF, building a model that represents correctly the PSF that would be measured in a microscope? Is that what you mean? Which accuracy? The estimation of the position or the shape of the PSF? The shape. Okay. So, okay, that's a good question. The question was, how do we build a good model of the PSF, and how do we know whether it was good? So, the way we do it is we didn't invent this. We take a z-stack. So you measure the PSF at different positions, and then it turns out that there is enough information in this to do something that's called phase retrieval. Phase retrieval is a process where you take real space images and you output the Fourier plane that corresponds to them. So you're asking, what is the Fourier plane phase mask or pupil plane pattern, if you don't have a phase mask, that would generate these images upon this and this defocus. So you need to know by how much you defocus. And there's an iterative algorithm. We do it very efficiently by an algorithm we produced in the lab. It's called Viper, V-I-P-R. If anybody wants to, it's very fast and it works. The nice thing, it works on each pixel in the pupil plane separately, not on Zernike modes or anything like that. And it's very efficient because of the way it was just implemented. Many things were just done by FFT, which is really fast. Okay, lots of math, but at the end, it's very fast. So then we have this model of a bead on a z at position 0, z equals 0, but defocused. Okay, and this is enough to give us the model of the pupil. From this model of the pupil plane, we can simulate what an emitter would look like inside some medium, even with a different refractive index. Okay, so we can simulate a bead, an emitter 5 microns up, even though it looks nothing like any of the images we took of the calibration measurements. So this is how we do it. And then once you have this model, you can look. Does it? You have a z-stack, you have your simulated z-stack, and you see how well they correspond. How do we? You can do some distance measurement between the shapes. Okay, so that's how we do it. Yeah. So I have a slide about that. I hope I have a slide about that. The question was, what's the difference between a 5 micron tetrapod and a 20 micron tetrapod? I used to have this. Anyway, the difference is that a 5 micron tetrapod. So first of all, in the phase mask, what the difference is that these peaks and valleys are just bigger for a larger range. And what does this translate to in the shape of the PSF is that the PSF is much larger. And when it's closer to focus, it has some different features. Instead of 4 spots, it could have 8 spots and so on. But basically, it's much larger. And so it needs more photons to be visible. So if you want to do SMLM on 20 microns, it's going to be very, very impossible. Okay? But if you want to do it on 4 microns, then you can do it. And you ask what is the best PSF to do it with. Okay, so, okay, that's all. That's the whole talk. Okay. Yes. Yeah, yeah. Okay. Until the last word, I thought I understood your question. So you're saying, I thought what you're asking is, you have your aberrations in your microscope. You can include that in your simulation. You measure them, and you include that, and then you optimize a mask that is optimal for this microscope. Is that what you meant? Okay. This is boring. Okay. Yeah. Yeah. Yeah, yeah, yeah. Okay, so yeah, so what you suggested is not boring, and this is what we do actually. So the final step of the training, you can just add your really measured model. I think Jonas Ries said this yesterday also. To get really good results, you have to get a very good model of your microscope. Okay, so you can take this network, add a few training steps using the actually measured PSF or the model derived from that actually measured PSF, and then train it on really the PSF that you really have. Modeled, okay? So it is simulated, but that's really, I'll show you, come later, I'll show you images. It really looks like what you measure in the microscope. Uh-huh. Okay. Uh-huh. Uh-huh. Why did it happen? Ooh. Uh-huh. Well, fortunately, there's an easy way to compare PSFs. You can do it by simulation, you can do it by experiment, and you can see which gives you better precision. Specifically about the double helix, it's wonderful. It's a great PSF. When it was optimized to give you the best results given that you want 2 rotating lobes. This was an assumption. This was prior. And then, given that it's 2 lobes, you can optimize and get the best results that 2 lobes can give you, that rotate. But if you ask a more general question, I don't need 2 rotating lobes, I don't care. Just give me whatever phase pattern, then you end up with the tetrapod, and it's, okay, I'm never gonna say it's a global minimum, because it's a very difficult optimization problem. Of course it's a local minimum, but it's lower than the double helix. We have comparisons in the paper. How is the PSF generated depending on the density? What do you mean? The learned PSF? So at low densities, so okay, when you learn the PSF, you have to seed with some initial PSF or nothing, which is also an initialization. For low density, for example, if you start with a tetrapod, it doesn't change much. But for higher, it would allow itself to be larger, a larger footprint. The PSF wants to be big to encode the information. Unless something is bothering it, like SNR or density, it will be big. It's more interesting when you use very high SNR, because then it can go wild and do whatever it wants, and in reality it won't work, because we'll never see this pixel change, in any reasonable SNR. Okay. Okay, thanks.
Un, deux. Un, deux.